In this second video lecture, we will be exploring some of the foundational concepts to statistics. We will begin with samples and populations, then move to sampling, and then to quantitative designs. Let's begin with samples and populations in part 1. As you can see from the figure in front of you, we will be learning about the large circle, the population, and also the small circles, the samples taken from that population. Usually in research, we examine samples and try to make inferences based on that sample to the overall population. So why do we do this? Well, it is not possible usually to conduct research with entire populations. Let's say I wanted to investigate people with depression. I wanted to try a specific treatment approach, say with people with depression. Well, it wouldn't be possible for me to try to find everyone in the United States who has clinical depression. That would take my entire lifetime. Perhaps it wouldn't even be possible to do that. Instead, it is usually more manageable to conduct research with samples taken from that population. So, instead, we try to make reliable generalizations from a sample to the population. Let's say I take a sample of people who have depression, a sample size of, say, I don't know, 300 people who have depression. I would hope that that sample would somehow be representative of the population so that I could say that, hey, the people in my sample, let's say that they felt less depressed as a result of my treatment method, that all people with depression would also benefit from this treatment method. That would be my hope, that I could make that generalization from the sample to the population. This fix is imperfect though, because each sample has a great deal of variance. For example, not every person with depression is the same, and so you have variance that is called within group. So you have in your subsample, let's say, in your sample, a variety of people with depression, and they're not all exactly the same, and therefore there is some variation between people in terms of how well they respond to my treatment. In addition to that, let's say that I took one sample of people from a population. I could hypothetically take a second or a third, and so on. Those samples may differ in how much they respond to my treatment approach. And this variation, both within group and between group, is known as error. So how do we fix this? How do we make sure that we have less error there in our study? Well, to do this, we have to increase the sample size. If we have a larger sample, there is less of an impact of error. Let's look at an example to understand this. Let's say that we want to know how long a depressive episode lasts for people in the United States. That's our population. People in the United States, how long does depression last? It would be impossible to know the length of a depressive episode for every person in the United States. As I mentioned, I could try to do this. It might take a lifetime. It might not even be possible to find everybody. So instead, we might take a sample of people with depression from, say, Seattle. Length, that would be our sample, by the way. Length of depressive episode would vary within the Seattle sample. Not everyone in Seattle is going to have the same length of an episode. It would also vary between samples. So, for example, if compared to a sample of people with depression from Detroit, this variation is called error. Remember our magic number of 30. We will be learning about this in just a moment. If the Seattle sample is large enough, its distribution is believed to mimic what's called the normal curve, which we'll be learning about in a subsequent session, and thus the overall population, which is also believed to mimic the normal curve. The normal curve, or the bell curve, is a way by which we can make sure that our sample is representative to the population. So to reduce the influence of error, we increase the size of our sample, and by increasing the size of our sample, we are better able to fit our data to the normal curve, meaning the more people you have, the more likely it is that they're going to fit the normal curve. So that's part 1. We just went through samples and populations. You may be confused about what the normal curve is. What you really need to understand for now is that if you increase the size of the sample, you are more likely to represent the normal curve, and that typically in research studies, instead of studying the population, we usually study samples and make generalizations from the sample to the population using the normal curve. That sets the framework for next session when you learn about the normal curve, or the normal distribution, I should say. Okay, part 2, sampling. So how do we get a sample of people in our research study? Well, there are a variety of approaches to sampling. Some of these are less complicated, though less reliable. For example, convenience sampling gathers data from a readily available sample, such as people with depression in a clinic you are working at. Those people are easy to access, they're at the clinic already, they're readily available. But convenience sampling is not the most reliable because you're not making sure that those people are representative of the population. They may be very specific to the kinds of people that you see. For example, they may all be very affluent, as an example, or they may be all women, as another example. That's not representative of everyone who is in the population, nor everyone who seeks counseling services. The best method is randomized sampling because it is less prone to error or bias. There are various forms of randomized sampling. One of these is cluster sampling, which gathers data from randomly selected pockets of the population, such as people with depression in randomly selected US cities. So you would select, for example, different types of cities in the United States, and those randomly selected people from those pockets would be part of your sample. In our Seattle sample, we may randomly select people from different neighborhoods, for example. This is called cluster sampling. The randomization helps to make sure that we have a representative sample, because the more random we are, typically the more things resemble the normal curve than if we engage in what we just talked about, which is convenience sampling. Stratified sampling is even more targeted, which is a randomized way of ensuring the selective sample adequately represents population demographics. With a stratified sample, we would again randomly select people, let's say from different Seattle neighborhoods. But we would also make sure that we had a certain percentage that met various demographics in the population. So let's say that I needed, I'll say 20% of people as African American, because there are 20% of people in the Seattle area or in the United States, whatever I was basing my population on, who were African American. I'm just making up that number, it's just an example. If I was to do that, I would randomly select people who are African American up to that 20% mark, and then not accept more than that. So I'd make sure that I had 20% of people who are African American. That is stratified sampling, which makes sure that you meet those demographic descriptors as part of your sample. So that is sampling, a very brief introduction to sampling. Let's learn next about quantitative designs. We're going to be learning about treatment and control groups here. We're also going to be learning about the scientific method. So this is kind of a joke, but it's hopefully it'll introduce you to the scientific method. The first upper version is what the scientific method is meant to be. The actual method is what may well happen. So in the scientific method, we observe natural phenomena, formulate a hypothesis, test a hypothesis via a rigorous experiment, modify the hypothesis if we need to, and then establish a theory based on repeated validation of results. So we see something happen, and over time we postulate that we have observed something occur, therefore we have a theory of why something happens. The actual method may be that we make up a theory based on what our funding agency manager wants to be true. We design minimum experiments that will suggest theory is true. Then we publish a paper, rename theory a hypothesis, and pretend we use the scientific method and defend theory despite all evidence to the contrary. Again, this is a bit of a joke, but you can see here that if you're going to be doing real research following the scientific method, typically you should be observing natural phenomena before you begin to develop theory. That is not always the case in counseling research. We have tended to be a field that is written about theory and then tried to defend our theory based on whether or not it's effective just by testing it out. But we have not always followed the scientific method as a field. So what kinds of research methods are used in counseling and psychotherapy? Well, there are two main types of quantitative designs: exploratory kinds of designs. These are things like survey designs, where we don't really have hypotheses, we just want to know the amount of people that respond a particular way to a variety of questions we might have. And hypothesis testing, which does use our hypothesis to test out whether or not our initial hunches are true or not. We have true experiments. These are sometimes called randomized controlled trials, quasi-experiments, ex post facto studies, and single-case experiments. The most commonly used quantitative design in counseling is the true experiment. Quasi-experiments are also fairly common as well. So what is an experiment? Well, experiments involve an independent variable, sometimes contracted to IV. An independent variable is something that in experimental designs can be manipulated by the researcher, and in non-experimental designs is not manipulated by the researcher. These are known as correlational designs. It can be categorical, for example groups, or continuous, known as a string variable. Group variable is when you just have a dichotomy, so for example group 1 or group 2. So let's say you have treatment or no treatment. And then continuous is, so for example, it might be the number of sessions that you have, that you receive. The dependent variable, known as the DV, is never manipulated, naturally occurring, and it is hypothesized that changes in the independent variable cause changes in the dependent variable. It must be continuous and not a categorical variable, known as a string variable. So, going back to IV, if you look back just a few moments ago, there was an image of a person eating lollies or sweets. And you saw there that the person, as they ate more sweets, the bag got smaller, their weight increased. And our hypothesis may have been that the more sweets a person eats, the greater weight gain that occurs. In that study, the independent variable would be sweets, and the dependent variable would be weight gain. True experiments rely on two core features for causation to be established. Causation means that we have an understanding about whether our treatment approach, for example, really caused changes in the dependent variable, so the IV directly affects the DV. To do this, we use randomization and what's known as control. Randomization of sample participants, for example randomly selected and assigned to one of two groups, a treatment group and a control group, reduces the likelihood of error and bias. Randomization, as you learned about in your sampling section from just a moment ago, is really all about understanding that if you don't randomize people, if you don't randomly select people into groups, it's possible that if you use convenient sampling, for example, you may not have a representative group of people, and that increases the risk of error and bias. Control groups, help to establish a comparison with random error to ascertain whether a difference or an effect was actually found or not. So if you have, for example, a wait list, or if you have another treatment that you're comparing your intervention with, say cognitive behavior therapy with person-centered therapy, you have some kind of a control group by which you can see whether or not changes really occurred based on your independent variable, or whether they're just caused, they would happen regardless of your independent variable. So in our two examples, let's say I had CBT and waitlist for people with depression. If I saw a reduction in depressive symptoms that was the same among the waitlist and CBT, that's very useful to know, because then I know that the reduction in depression symptoms from the first time that they were measured to the second time they were measured is not based on CBT itself, it's just based on some other factor because the waitlist has the same effect. It's the same with CBT and person-centered. If I have the same effect happen, the same reduction in depressive symptoms between the two measurements, I cannot say that CBT causes a reduction in depressive symptoms because person-centered had the same effect. So controls are very useful for us because they help us ascertain whether the independent variable was the reason that there was a change in the dependent variable. By comparing changes in the outcome variable, the dependent variable, with the predictor variable, the independent variable, and a dud version, which I just talked about, treatment as usual, wait list. Treatment as usual, by the way, is something that is provided in the community, so if you go out and receive community-based services, a placebo or a sugar pill is something like receiving some kind of a sham treatment, for example, that, it isn't really counseling or psychotherapy. We can ascertain whether the findings were merely caused by chance or random error. This helps us to establish what's known as causation. It doesn't necessarily prove causation, but helps us to establish causation. If the dependent variable changes in ways that are different from the dud version, we can claim that changes in one variable cause changes in the other. So the graphic here, the person says, my stomach hurts. Maybe it was the bad tuna I had for lunch. Too bad I don't have a proper control group. Now I'll never know. It may well be the tuna, but it could be something else. And if we don't have some comparison, we can't necessarily ascertain the results are caused just by what we hypothesize. So here's a graphic example of this. Let's say we have a random assignment of participants to groups. We have an intervention group and a control group. The intervention group gets CBT, the control group gets a wait list. They just wait until they get CBT, they get no treatment. We are looking at, in our dependent variable, depression scores, and let's say the Beck Depression Inventory, which is a very famous inventory for measuring depression. And we are going to gather data from before treatment and then after treatment. So let's say the treatment lasts for 15 weeks, so it's 0 weeks and at 15 weeks. Controls help us to reduce the possibility that changes will likely occur because of confounding. In counseling, there are many unwanted influences on the dependent variable, including things like the client's level of motivation, show rates, how often they come to therapy, and life circumstances. Life circumstances, there are a whole lot of examples of this. They could be things like marriage or divorce or the birth of a child or the loss of a job, just as some examples. Unfortunately, many action research studies, things that you would do in a practice setting, cannot include randomization or control groups for ethical reasons. Here's an example. When I was working at an inpatient psychiatric hospital, I was unable to say to some patients, hey, I'm going to randomize you into one of the treatment groups so that you get the better treatment or not, or you get you don't get the real deal. You can't really do that with people who are hospitalized because they tend to be in fairly significant need and you can't withhold treatment to them. Same with control groups. You can't say, well, I'm going to have 2 control groups, one of which is going to get the real deal, another is not, and oh sorry, I know you're an inpatient, but you're not going to get the real treatment. Can't really do that. In these kinds of examples, we would use an experiment known as a quasi-experiment, which just usually collects pre and post data and just compares the sample against itself. So here, we would essentially be just using the same inpatient sample and just collecting data pre and post and just comparing how the sample did against itself. This lacks the rigor of having a control group, but sometimes is the best that we can get. Sometimes we also want to examine existing data. This is known as historical data. This research is called ex post facto, or after the fact. It's Latin for after the fact. Ex post facto research is also used when we cannot conduct experiments with certain populations for ethical reasons. So we can't do our randomization and controlled experiment. Here's a couple of examples of this. Birth abnormalities and cancer. You cannot tell mothers, I want you to engage in this type of behavior, like for example take a pill that's known to cause birth abnormalities, or I predict will cause birth abnormalities, because that's not ethical. You can't tell mothers to basically risk giving their children or their baby, their fetus, a birth abnormality. Same with cancer. You can't tell a person, hey, I think that smoking causes cancer, therefore I want you to start smoking and to do that for the next 20 years to see if you'll develop cancer. Not ethical. Can't do it. So instead, you conduct ex post facto studies which look at whether or not change occurs in a historically existing sample. So with birth abnormalities, we would be investigating whether or not the mother was taking certain medications during pregnancy and whether that caused birth abnormalities. We'd be using an existing data set. Same with cancer. We can't necessarily tell people to start smoking, but we can gather data from smokers and non-smokers over a long period of time to see if there are differences in rates of cancer between those two groups. We would do that again with an existing data set. Whenever you have historically existing data, this is called ex post facto research. Quantitative designs also include single case designs, sometimes referred to as n equals 1. N is the sample, so an n equals 1 means a sample of 1, which use baseline conditions to compare scores with and without treatment. Almost like a pre and a post test, behavior is charted using frequency counts most commonly. This is an evidence-based practice when working with children with autism spectrum disorders. Applied behavior analysis, or ABA, uses single case designs almost exclusively. Here's a visual example of a single case design. So let's say you have a frequency of disruptions maybe in a classroom setting or a home setting. You have a baseline, so you have here on the bottom axis, known as the x-axis, the number of days, so day 1, day 2, day 3. You just allow the child to engage in the behavior they usually engage in, and you count the frequency of disruption. So they have 7, 6, and 7 disruptions the first 3 days. Then day 4, you introduce a new condition whereby you praise them when they engage in appropriate behavior that you want. And here you see a lower frequency of disruptions during that period. Afterwards, you withdraw the praise, and after you withdraw the praise, they go back up to baseline to some extent. And so you can see here from just using this data with the same person that we can figure out whether or not an approach is effective for that person. Single case designs can be very useful if you're comfortable with gathering behavioral data, because it's going to give you information that is specific to the client you're working with. Let's learn a little bit about hypotheses and what they are. If you remember from your early days of taking research and learning about the scientific method, hypotheses are educated guesses about what will occur in an experiment. You probably learnt this from a science class back in the day. They are used in quantitative studies. So there's a funny graphic below of two foxes. It looks like a male and a female fox, though I can't really tell. The one fox turns to the male and says, pinch. The other one, or at least pinches the other fox. That fox says, ow, looks at the pinch and asks what that was about, and the other fox says, I'm testing the hypothesis that comedy equals tragedy plus time. Kind of a goofy example. But we develop these theories, these hypotheses of what happens in reality, and we need to test those out, and the way that we do that is through experiments. Hypotheses include an independent variable, which we talked about, that is known to cause change in a dependent variable, for example, employment rates. So we want to know whether our independent variable causes change in, say, rates of supported employment. The null hypothesis is the lack of impact on the independent variable. So this would be no change compared to random error, for example, placebo, treatment as usual, or waitlist. So in other words, that our hypothesis has no effect, that say we implemented our supported employment intervention, or going back a few minutes, CBT for depression. Let's say that we were doing CBT for depression. The null hypothesis would be CBT has no effect on depressive symptoms. An experimental design begins with the identification of a hypothesis. First, we identify our hypothesis, which may be that CBT is going to cause change in depressive symptoms. Then we identify a null hypothesis. So, for example, well, the flip side of that is going to be actually it's possible that CBT would cause no change in depressive symptoms. Then we identify a level of acceptable risk known as the probability value or p-value. Typically this is about 5%, and you'll learn why in a subsequent lecture. Then we test our results with statistics and decide whether the hypothesis or null hypothesis was correct, based on that 5% rule. So hopefully this makes vague sense to you. It'll become clearer as we actually begin testing out some hypotheses, and start to learn about that 5% in a subsequent lecture. And we just reviewed samples and populations, sampling, and quantitative designs. This concludes the video lecture.